Today's distinguished speaker is Bill Swartout. Bill is the Technology Director at the Institute for Creative Technologies at the University of Southern California and is a research professor of computer science, also in the computer science department at USC. He's received his PhD and MS in computer science from MIT and his bachelor's from Stanford. Bill's research interests include virtual humans, explanation and text generation, knowledge acquisition, knowledge representation, knowledge sharing, education, intelligent agents, and the development of new AI architectures. Bill is a fellow of the American Association for Artificial Intelligence and has served on the board of counselors for the AAAI. He's past chair of the Special Interest Group on AI for ACM. He is a member of the U.S. Joint Forces Command Transformation Advisory Group, the Board on Army Science and Technology of the National Academies, and a past member of the Air Force Scientific Advisory Board. Particularly excited to have him here today because he is my academic grandfather, being the advisor of my advisor. With that, please join me in welcoming Bill.
Michael, thank you very much for that nice introduction. I'd like to tell you a little bit about, start off by telling you a little bit about the place that I'm coming from, the USC's Institute for Creative Technologies. And the ICT was founded about 8 years ago and was designed to be a place where entertainment could meet technology. In particular, were funded by the U.S. Army, and they were interested in exploring the question of suppose that you had people who were really expert in modeling and simulation and understood the underlying technologies that go into that, such as artificial intelligence, graphics, immersive displays, and interactive media, and had them work alongside people from the entertainment industry, people who understand story, how to create characters that we find compelling and engaging, and understand games and how to do production of large entertainment enterprises. Would it be possible, by having those two groups work together, to create training systems that were really engaging and compelling for people to experience? So that's kind of been the hypothesis that we've been exploring these last 8 or 9 years or so. And the goal has really been to try to create synthetic experiences, virtual experiences that people react to as if they were real. Well, early on in the history of the ICT, the Army came to us and they said, you know, what we would really like you to build for us is something like the Holodeck. Now, many of you Trekkie fans out there will remember the Holodeck from Star Trek, which was a place on board a starship where you could go to experience a virtual environment. There were virtual characters you could interact with, a whole total environment. And it could be used for a variety of purposes, ranging from training or education to even entertainment. So we thought that was a great idea. It was a great idea for a couple of reasons. First of all, it really suggests, as a metaphor, a lot of the research vectors that you're going to have to explore in virtual reality and simulation. And the second thing is, Star Trek is actually set in the 24th century. So we figured it'd be a long time before anyone was actually asking us for any deliverables. Okay, so we turned out to be wrong about that. But it does, the Star Trek does suggest some really interesting research vectors that you have to explore. So if you're going to build something like the Holodeck, what do you really need? Well, first you need photoreal graphics. You need to really be able to give people the feeling that although it's a virtual environment, you're really there. You need immersive environments that can envelop the participants and make them feel like they're completely engaged. And you need characters that people can interact with, virtual humans. And you need a compelling story. So as I go through this talk, clearly, you know, this list of technologies together with the story aspect, clearly this is a very interdisciplinary effort. One of the things that I want to point out, and I'll bring this up several times through the talk, is that we've really seen some synergies emerge from the convergence of both these technologies and from the convergence of content with the technology. And I'll be highlighting some of these as I go through the talk. Okay, I'd like to begin by talking about photoreal graphics. And this is work that's being done at the ICT Graphics Lab. Paul DeBevick is the leader of that effort, and there are a number of other researchers who are involved with him as well. The goal of the ICT Graphics Lab has been to advance the state of the art in graphics technology to produce realistic virtual environments, realistic characters, and integrate both real objects and synthetic objects into a common environment. And we want to be able to achieve and surpass the photorealism that you currently see in video games and in Hollywood movies without having Hollywood budgets or Hollywood production timelines. In other words, we want to do it cheaper and quicker. And do the whole thing so that it renders, at least, in real time and make it rapidly reconfigurable. Now, Paul began working in this area when he was at Berkeley as a graduate student, and his PhD thesis was about a system called Facade. And at the time that Paul did his work, which was in the mid-90s, most of the 3D computer models that existed were created by artists, and they consisted of having lots and lots of polygons that got rendered by a computer to produce output. The question was, that Paul asked himself was, could we use photographs, take photographs of a scene, and then use those to actually build a 3D model much more rapidly? And so basically what he developed in this Facade system was a capability to do exactly that. You would take a photograph of a building, or several photographs of a building, and then from those photographs, using a tool he developed, create a relatively simple, almost cutout-like 3D model. So instead of having all the detail that you would typically expect to see in a model like this, it's basically just a very blocky sort of structure. The idea is that given that blocky structure and the photographs we've taken, when we wrap the photographs around the building, you start to recover some of the detail that was missing. And by taking this approach, it's much more rapid to both build the model and to render it back out. And here's a little video that showed how this worked to capture the tower at the Berkeley campus. These are some of the photographs. Can we bring the audio up a little bit on the video? There we go. So here's the simple 3D model. When you add the image data in, the whole thing just comes alive. Okay, so this was great. This gave you a way of going out, taking a bunch of photographs of an environment, and then creating a 3D model that corresponded to it. Now, suppose that you wanted to put into that world now some synthetic objects. Well, the problem is that most of the time, if you put synthetic objects in, they're going to stick out sort of like a sore thumb. And the reason is because the lighting that's used to light these synthetic objects when they're being rendered in the computer is not the same lighting that was used when the photographs were originally taken. So Paul developed a technique, and it's actually a very elegant and simple technique for recording the light that was used to take the original photograph. Now, if we were in this room, you know, the kind of light information that you want to have is there's a lot of strong lights coming, for example, from the overhead lights up here. But then there's also light that we're getting off the screen here. There's bounce light that's coming off the walls back there. We really want to capture all of that light. The approach Paul took was basically to take a silver ball, much like the ball that some people have in their gardens in the backyard, put it into the scene, and then take a photograph of the ball. And because the ball is essentially giving you a 180-degree view, you can see where all the light is coming from. You take actually multiple exposures, so you get both the dimmest light that's on the scene, as well as much more high-intensity image information. And from that, you basically have then a model of where all the light is coming from in the scene. And here are some examples of different real-world environments that he captured. This is outside the Uffizi Gallery in Florence, Italy. This is on the beach. This is in a eucalyptus forest. This is inside a chapel. And if you then use that lighting information to actually render the scene, as you see, you get it now so that the synthetic objects really look like they belong in the environment that they're now embedded within. So this gave us a way of taking synthetic objects and embedding them into one of these 3D models that we captured using photographs. Now, the next question is, suppose you want to put people into one of these environments. How do you do that? Well, you know, it's a synthetic environment, so you can't really photograph them in the environment. So what would you do? Well, Paul developed a device that's called the Lightstage. And what it is the first version of it was a large hoop that you see here that has strobe lights all around the rim of the device. And this device rotates around the person who's seated in the chair here. And while it's rotating, all of the strobes flash in sequence, and a video camera, which is out here, takes a picture of everything that's all of the different images that are being captured. So here's a time-lapse photo of what it looks like when this thing is operating. And that gives you basically a database then, all these images you've captured, of what this person looks like illuminated from all possible different points of view. And you can then use the additive property of light together with that data that we captured about the lighting conditions to re-render this person in a variety of different lighting conditions, like you see here. Well, so that's great, and it's photoreal, but it's not moving, it's static. Question is now, suppose we wanted to record a person in this environment and actually have them carry out a performance and then embed them in the environment. So that's a follow-on version to this earlier Lightstage called Lightstage 6. And what it is a very large geodesic dome about 10 meters in diameter that has high-intensity LEDs all around the edge of the device. And these fire very rapidly. We use a very high-speed video camera that runs at about 1,000 frames a second. And so as you're changing the lighting conditions, the person can also be moving, and you wind up getting about every 30th of a second a complete basis set of lighting conditions that can then be used to relight this person in a new environment. Here's a video that described how that system works. Took a lot of takes to get that one to work. Okay, so now we can take actual live performances and embed them into these synthetic environments. What we've also done is use the Lightstage to capture people so that they can be then used to create virtual humans. And I'll have more to say about that in a moment, but I want to show this one example of a character that we created first using digital artists, and that's the version that you see on the right. And it looks actually pretty good. And then there's a version that was captured photographically using the model that was used to create the artistic version. And you can see how much more photoreal that character looks. But both of them are now animatable characters, or the heads of animatable characters. So this is the photoreal. That's the artist rendered version over there. This is a character we built for the Army Accessions Command, which is the recruiting command in the Army. Okay, well, so now this is some of the work we've done in creating computer graphic systems that allow us to create photoreal environments. I want to talk next about some of the work we've done in immersive environments. And what we wanted, the goal here is we wanted to create an environment that people could really be in, that would stimulate all of their senses, allow them to move freely about in the environment, and would both allow individuals to be in the environment as well as groups. So you could have groups of people there, all of whom are rehearsing or carrying out a training exercise, as well as individual people. Now, at the time we started this, we looked around at what was available, and we really felt there were some problems with some of the existing technologies. There are head-mounted displays, there are caves. These are different approaches to creating virtual environments. The problem was, for one thing, if you want to physically recreate the feeling of walking around in one of these environments while you're wearing, you know, the 80 pounds of gear or so that the Army likes to go out with, it's actually quite difficult because, first of all, if you're in a cave, you actually can't physically move around in the environment. You have a 3D mouse, and it's letting you float through the environment. Well, if you're trying to train people in how to jump over things and stuff like that, that's not going to work so well. With a head-mounted display, one of the problems is most of them you're encumbered. They're not wireless, so there's a cable that's coming off the back of you, and there's a couple of graduate students who have to follow you around everywhere you go to make sure you don't trip over the cable. The other problem is that it's actually hard to, in either of these environments, to rehearse groups. A cave really only works for one person at a time because the perspective is only correct for that one person. That person has to be tracked. In a head-mounted environment, you can have groups of people, but all the people who are out there have to essentially appear as avatars in your display because you can't actually physically see them. So it just makes it more complicated to rehearse groups of people. The idea we had for Flatworld was to try to combine computer-generated imagery and sound with traditional stagecraft techniques and create an environment that was very flexible, but that also allowed people to move around and be in the environment. And this is next slide is a video that describes how that system works. Okay, so this is basically one of the approaches we've taken to creating these more immersive environments. Now, the next step is finding a way of putting in characters, virtual humans, that can populate this environment. And the idea here, the vision here, is I'd like you to imagine basically a simulated world with characters that are almost human. Specifically, what I mean by that is that these characters should be able to, first of all, they're unscripted. So they're not following a script that somebody's worked out in advance, but instead they are looking at what's happening in the world, reasoning about that, using some artificial intelligence, and figuring out how they should respond, what would be the appropriate response to make in that situation. They fully perceive their environment. So they're not only perceiving the virtual environment, but they're also ideally perceiving the people, the real people that they're interacting with. They interact using the full range of capabilities, both verbal and nonverbal, that we as people use. So it's speech as well as gestures, eye glances, all of that stuff. They can interact with the environment, and importantly, they can exhibit emotions. This is actually one of the things that we found was very important to give these characters a capability for. You know, one of the things we found is that people are very anthropomorphic. So we ascribe emotions to things all the time. In fact, we found that in some of the early prototypes of the virtual humans that we built, sometimes they would, there would be a bug in the software. The characters would be very slow in responding. And people looking at that would say, oh, I know what's going on. This character is actually really annoyed with you, and it's trying to figure out if it's going to tell you off or not before responding. Now, nothing like that was actually happening. But what this told us was that we've got to model the emotions, otherwise we will be sending the wrong cues to people. So that has actually been a big area of research for us, and one that is interesting because, you know, although AI is a field that's been going on for over 50 years now, if you think about it, very little has gone on in the area of trying to model emotions. Some, but not a lot. Mostly what people in AI have been concerned about is trying to build characters that are very smart. So a program that can beat you in chess, or one that can diagnose a disease or something like that. Basically trying to create Mr. Spock, you know, who is a great guy to have on your team, but basically an alien. And we felt that it was really important to address these emotional issues. And what we found is that by bringing in emotional elements, it's actually possible to solve some AI problems that are hard to solve if you don't have that. I'll have an example of that in a moment. So basically wanted to do all this, and the kicker is being able to do it all in a coherent and integrated sort of way. Now, 10 years ago, I'd like to give you a glimpse of the state of the art for where we were at. So this was basically a system called Steve that Jeff Rickel and some of the other people on the originally involved in the virtual human effort put together for teaching how to perform this task of starting up this large shipboard air compressor. And as you can see, there's quite a bit of room for progress here. And so the next effort that we did was a project called the Mission Rehearsal Exercise Project. And this is a project that we finished up about 3 or 4 years ago. I'm showing it to you first because it sort of gives a nice glimpse of how the technology is progressing. And secondly, because there's some things about this project that allow me to illustrate some of the ways that the integration of technology has been important. In its background, this project was designed to simulate a situation in Bosnia. The setting is Bosnia. You, the trainee, are a lieutenant in the United States Army. You're en route with your platoon to reinforce another platoon that's dealing with some civil unrest. And on the way, One of your Humvees gets into an accident with a local civilian car. There's a small child that's injured. There's a crowd that forms here in the background. There's a TV camera crew that shows up and starts filming everything. And now you, Lieutenant, have to figure out what to do. Do you stop and render aid? Do you continue on with your mission? You know, if you don't continue on with your mission, people are going to be upset. So all kinds of problems. And here's a video that shows how that system worked. Okay, so obviously bringing off something like this involves a lot of different research projects. You've got to have, speech recognition, natural language, speech synthesis. You have to be able to reason about the task and the domain, emotions that I already talked about. You have to be able to generate gestures, so a lot of different things going on. Putting all of that together is obviously by itself actually a big research task, and making all of that work. I'm not going to have time to talk about all of these issues, but I do want to talk a little bit about how we model emotions in this system, because that's kind of one of the newer things. And we use a theory here, a psychological theory that's called appraisal theory. The basic idea says that we as people are always looking at the world out there, and if you find yourself here, you're evaluating perhaps, where you are now against your own internal goals and beliefs and desires and so forth. And if you'd really like to be, there, you're going to react. You're going to feel, a bit of frustration possibly. So a little more formally, this appraisal theory says that we're constantly forming these appraisals based on comparing the environment out there against our own internal goals and beliefs and intentions. And this evaluation is expressed in terms of things that are called appraisal variables. So basically we're looking at, is this event that's happening desirable? Is it expected? Is it controllable? Can I control it in any way? And is there some causal attribution? Can I blame it on somebody else? And then it's from these appraisal variables that what we think of as conventional emotions are actually derived. So if an event is undesirable, not controllable, and uncertain, that tends to lead to a feeling of fear. If it's undesirable and a for sure thing, that'll lead to a feeling of sadness. If it's undesirable and somebody else is at fault, that will tend to lead to a feeling of anger. So this is how these feelings, these emotions are derived. Now to make this more specific, let's look at the case of our friend the sergeant from the previous video and evaluate the accident from his perspective. Now, he would really like for the child to be healthy, but that's not true. And that, together with the fact that the blame for this accident is unresolved, leads to a significant feeling of distress on his part. Now, hold that thought for a moment. I want to return to this issue of integration. Remember that I said that we're bringing together all these different technologies and that's a big job. But the interesting thing is that by bringing together all of these different kinds of information, it actually makes certain kinds of problems easier to solve because it makes additional information available that wouldn't be there if we were just looking at this from one narrow perspective. For example, from a particular perspective such as natural language understanding. Let me illustrate that with an example. So the problem that we're going to look at is the problem of resolving the focus of an ambiguous question. Okay, so here's the question. Okay, now to us, the answer here is obvious, right? There was an accident. Anybody can plainly see that, okay? However, if you're a computer, it's not so obvious because, in fact, there are a lot of things that just happened here, okay? Well, now, all of a sudden, it's a little more difficult, isn't it? It's hard to know, which of the answers of these is the right one to pick. Well, people who work in natural language understanding have actually identified this problem. They know all about this problem, and they've developed some heuristics for dealing with it. One of the most common is to use the idea of recency. It says basically the thing that happened most recently is probably the thing that's in focus. And that actually turns out to be a quite good heuristic. In this case, though, it gets you the wrong answer. What we realized, though, was that actually we may have our hands on a stronger heuristic here. And the idea is basically, suppose that we look at the emotion model that is in the system. Now, one of the things our emotions do is they focus us. So we think about, if you're upset about something, that's what you're going to be, obsessing about. And you can certainly see that in language, that Freudian slips, essentially, when people are upset about something and a appropriate opening is given, boom, that's what they want to talk about. So, okay, so using this additional information that we get from the emotion model, we know that the sergeant is upset about the accident, and all of a sudden, we have our answer. And it's the one that corresponds to how people would interpret this. So interestingly here, by bringing in this emotion model and this additional capability, it makes it easier for us to solve something that is quite hard if you just look at it from a particular stovepipe of natural language by itself. Now, moving beyond this mission rehearsal system, we asked ourselves the question, could we use virtual humans to teach more complex skills than just maneuver, like you saw in the previous video? Like, could we teach virtual humans to teach people how to negotiate? So we put together a demonstration system, and the idea is basically the setting for this is somewhere in Iraq, and the background is that operations have been planned in the area of a relief clinic. Your job is to go and your job as an Army captain, in this case, you've been promoted, is to go and persuade the doctor running the clinic and a town elder to relocate the clinic without revealing any of these operational plans. Now, there are two characters that you have to interact with here, and if you play your cards right, you can actually get one to convince one and then get him to help convince the other. And if you don't, it'll be more difficult for you. The virtual humans, what they're doing is when you say something to them, they're appraising what you said in terms of their own internal desires and beliefs and figuring out, is this a good thing? Is it a bad thing? How should I react? And then they're using some psychologically based models of how people resist negotiation to interact with you. So here's a video of that system. Okay, so I want to now turn to story. And one of the things that we really found made things work much better was having a compelling story that underlies these scenarios, a background and the story itself. And when we originally started working with the Army, we would talk to them about their simulations and say, your simulations would be a lot better if you had a really good story underneath these. And they'd say, what do you mean? We have stories, first this happens, then this happens, and then this happens. And we say, no. That's not a story. That's an event list, okay? A good story is really a much richer thing. It has a structure. There's emotional engagement. There's a dramatic arc. So you introduce the situation, you introduce a dilemma, it gets developed and ultimately resolved. You've got to do that. And there are surprises. Things go wrong as you're, the most boring story is where everything goes right, okay? And in fact, though, if you look at some of the Army simulations, actually, one of the things they often try to do is have everything go right. And so it really, it was really an interesting, I think, epiphany for them to sort of see this notion of story and the importance of it. Now, a good story can really do a lot of things, particularly in the environment of these computer-simulated environments. First of all, basically, it creates a very strong context that limits what people are going to say or do in the environment and really makes virtual humans feasible because it means that you don't have to program the virtual humans so they can do anything or respond to any situation. Instead, it basically creates a micro world, and you can operate within that. So in the context of the doctor scenario, yeah, you're going to talk about the marketplace, you're going to talk about the clinic, you're going to talk about safety concerns maybe or medicine, but you're not going to talk about how the Dodgers did last night. Okay, so that context really helps in making these feasible. Secondly, it creates an emotional involvement and engagement with the characters. Interestingly, it also, we found from a technical standpoint, it can force some new research issues. If you think about it, most of the work that's gone on, not all, but most of the work that's gone on in natural language understanding has essentially assumed that you're on the phone talking to a computer about some sort of a essentially database kind of problem or request. So, get me 2 tickets to the next Laker game or something like that. What we found here in working in these scenarios is all of a sudden you've got to deal with things like multi-party natural language. So you've got to understand, when I'm talking to you and when I've stopped talking to you and when I've started talking to you, and all of that has to be modeled and understood by the system. The other thing is most of the work in natural language understanding has followed Grice's maxims, which, among other things, say that basically in interacting through natural language, you're supposed to be cooperative. Now, generally, in many situations, that's true, and Grice's maxims are a great thing. But, in fact, if you get into certain situations, like a negotiation, you're actually dealing with uncooperative communications often. If somebody comes to you and wants to your front door and wants to sell you something, what you're trying to do is figure out how you can get out of that conversation as fast as possible. At least that's what I do. So you're basically dealing with a very different sort of communication that you need to model. Finally, if you choose the story properly, it can actually help cover or hide some of the underlying technical limitations. So, for example, we used a Spanish doctor in this scenario because we knew that the natural language understanding and the speech recognition were not going to be perfect. And so if you're talking to somebody who is supposed to be a foreigner, it's plausible that he wouldn't always understand language and that he would occasionally get prosody wrong or pronunciation wrong when he was speaking back to you. So that was good. But if it was somebody who was, supposedly from California, it would seem odd that they weren't understanding it. Or maybe here from an East Coast perspective, it wouldn't seem odd at all. I don't know. But at any rate, the idea is by cleverly constructing the story, you can really cover a lot of the limitations or deal with them in the underlying technology. But some important issues that come up in using story in interactive environments, and this is an area that Michael Young and Mark Riddell have really been looking at very seriously, is that in fact what we're used to in stories is traditional linear story structure. So watching a movie, reading a book, that sort of thing. And most of the tricks that we get out of storytelling assume that kind of linear environment where the writer basically controls everything. So he's controlling what all the characters are saying. Now, in an interactive environment, all of a sudden you don't have that. Basically, you can control what the computer-generated characters say, but the guy you're interacting with can say whatever he pleases, and you've got to be able to deal with that. So for us, since we're interested in training, one of the big issues is how can we make sure that the trainee doesn't just sort of take the scenario and go over the hill with it and never come back or never have the right pedagogical experiences. And the solution seems to be to have in the environment an active direction component. So basically, you need to shape the story to build in essentially bumpers so that there are certain kinds of things that you can do and certain kinds of things that are more difficult. So you basically use the environment that you're in, the non-player characters, and possibly a coach character to limit the range of things that, that people can do. And if any of you have seen the movie The Truman Show, it's a great example of exactly what I have in mind here. This is it's a story set where there's this character, Truman, who is growing up in this large bubble, very large bubble. And the only people that he interacts with are actors who are playing the part of townspeople in this town. And the environment that he's in is also completely under the control of a director who can manipulate it and create new experiences. And throughout the movie, basically, the movie is about Truman essentially figuring out partway through that something's not quite right with this environment. This isn't the real world. This is somehow a manipulated environment that I'm in. And the story is really about the struggle between the director to continue to maintain control and Truman, to break out. So it's a great movie for kind of understanding a lot of the issues that arise here, I think, and serves, again, like Star Trek, a very nice metaphor. So I wanted to close here with a few thoughts on what we've learned from Hollywood as we've gone through this exercise. And the first thing is actually, and this is a good bit of news, is that when people are in these simulated environments, they actually want to believe. They really want to, as long as you don't overly violate the temporary suspension of disbelief, people will really want to be in the experience and be part of it. This is actually something that some people from Universal Studios pointed out to us who were involved in the development of location-based entertainment, of theme rides, essentially. They said, everybody knows the ride isn't perfect, that it isn't a complete literal recreation of what it's supposed to be, but people want to enjoy the experience and they will play along with it. And basically, in any situation you're in, whether it be a TV show or a movie or reading a book or even in one of our simulations, people really do want to believe and they want to get engaged. So that's one interesting aspect. The other thing is that when you bring all these different elements together, it really does make, it does seem like the whole is greater than the sum of its part. That you really, all of them work together to create the experience. The last point is an interesting one. As engineers, we tend to like to, particularly academic engineers, we tend to like to latch on to a particular approach and say, boy, that's the way to go. I believe in neural nets, or I believe in rule-based systems, or I believe in this or that. That's the one true way to go. What we've learned from Hollywood is that actually often taking a mixed approach, a hybrid approach, is the most effective. And almost any modern movie that you go to now that looks like it's live action will in fact be some live action mixed with computer-generated graphics, possibly mixed with models. And if the filmmakers have been successful, you won't know. When you're seeing CG, when you're seeing real people, and the point is that why do they mix all these things together? It's not just because they like technology. Certainly far from it. It's because this is actually the cheapest and the most effective way to create the experience that they want to create. And so similarly, in the work that we've done, we found that, for example, natural language understanding, very hard problem. And you could try to approach all of it by doing very deep natural language understanding, where first you get the speech recognition, then you do natural language understanding to form a semantic interpretation, then you do dialogue modeling and all of that. But sometimes it's actually just as effective to take a much more statistical approach, where given a set of keywords that are coming in, you form a likely estimate of what's the best response to give in that particular circumstance. And that can be very effective. So we've sort of taken this idea to heart that having a hybrid approach is sometimes the best way to get the fastest down the road. So with that, I'd like to leave you with this thought. Thank you.
Okay, I'd like to first go to questions from UNC Chapel Hill. Are there any questions from you guys?
I don't know if we have, well, I don't know if we were able to ask a question. Sounded like you had a good question.
I can hear you guys. Are there any questions from you? Okay, we'll go ahead and move on to Duke. Duke, do you guys have any questions for Bill?
Hang on.
Can you hear us?
Yes, we can. Why don't you say who you are and where you're from? Because we can't see you.
This is Vince Conitzer at Duke.
Stay in your seat. I think he's making these.
Great, go ahead with your question.
Just over here. Could you say a little bit more about how this compares to modern computer games?
So actually, underlying this technology, we're using computer game engines. So the virtual humans that you saw are actually based at the lowest level on Unreal Tournament. And so we basically got UT and the UT game engine and have modded it essentially to support these virtual humans. And the advances rather that have been made in computer game technology have been a huge win for us, because basically it allows us to exploit this huge investment that the commercial sector has made in computer graphics and the underlying technologies, physics engines, and all of that, and not have to develop those ourselves. When we started the ICT up, the original virtual humans we developed were running on basically military simulation software, and you had to run it on SGI computers that cost like $2 million. And now, with the advances that have occurred both on the computer speed side and also in the underlying software from the game industry, we're able to run the last demo you saw of the doctor negotiation on a laptop, a big laptop, but a laptop. So the other, I guess the other point to make here is that I think that trend will continue. That we'll be continuing to exploit things that are going on in the game industry. At the same time, some of the technologies that we're developing, I expect, are going to move back the other way. Already, some of Paul's work on high dynamic range imagery has been incorporated into both graphics cards as well as some of the game engines.
Great. Are there more questions from Duke or Chapel Hill?
Vince. He's saying this microphone you can.
Okay, I have a question. On the two examples you showed in the end, it looked like you primarily had a participant, a true human military participant, trainee, if you will, interacting with a very large TV screen. How much are you having people in some of these more immersive environments that you were showing earlier on?
So we have, so the one at the end is basically an interaction with, in the context of a large monitor. But we also have characters that we've put into Flatworld that you can interact with that are life-size characters. And so the Sergeant Star character, which is one of the characters we've built, the one we built for the Army Accessions Command, is a life-size character, and people interact with that in real time, as a full character. Having the life-size character actually really seems to make a big difference in terms of people's feelings about the character and their acceptance of it. It creates more of an engagement.
Other questions from the remote sites?
I think that's all the questions for us.
Okay, great. Let's take questions now from here. And I'd like it if you guys could talk into these microphones when you ask questions remotely so that they show up on the audio.
Okay. So with the virtual humans, we saw appraisal theory and the different parameters that were used in giving kind of the personality of the character. So there's kind of a threshold when you have one emotion, one type of dominating belief or affect, and you switch to another emotion after having some sort of stimulus in the environment. So what I'm wondering is that sort of threshold for switching from one emotion to another, is that theoretically based, or do you have it more trial and error?
So the threshold that you saw was actually not changing the emotional response, but instead it was changing the selection of the coping strategy that the character used for responding to a particular situation. So I didn't get into that, but basically there are, when an emotional, when an emotion reaches a certain level, or when there's an emotional response to something, one of the things that the character tries to do, just like we as people do, and this is actually part of appraisal theory, is to deal with that through coping strategies. And there are two general classes of coping strategies. One is problem-focused coping strategy, where you try to make a change in the world. So the sergeant's, the medic's rather, initial recommendation that getting a medevac would be a good idea is a way of making a change in the world that will make the child better and reduce everybody's stress. The other kind of coping strategy, the general class, is a belief-focused approach. And there, you're not making changes to the world, but you're making changes to your own internal beliefs to reduce your stress about the situation. And so there, by essentially trying to blame the mother for the accident, it's like, I'm not so stressed out about it because now we know that, who was at fault in this case, and I'm blameless, So the thresholds that you were seeing are actually changing how that choice is made between the kind of coping strategy that you're going to use. Now, another question that you were sort of hinting at is, how do we know that these emotional models are really accurate? You know, I mean, is this the way that people would really react? And so Stacy Marcella and John Gratch did an interesting experiment, which is they took a clinical psychological tool. It's an assessment tool that's used to assess whether people have actually appropriate emotional reactions. And it's done through a story that's told incrementally. So you say, you know, okay, you're going to work and, you know, you confront your boss. How do you feel? And then it lays out, you know, the next thing that happens with your boss, and next thing, and each time asking you, how do you feel? And people, you know, tell you how they feel. So basically what we did is, or what John and Stacy did, is they encoded that in a machine-readable form, then ran the model on it, and said, okay, do we have, you know, a rational model or not? And found that out of about 15 different parameters, it was basically matched normal except for 2 of those. And I don't remember exactly which ones those were. But,
Thank you.
yep.
More questions?
I've seen a lot of these simulations. There were some people at RTI who did some work in this area, going back maybe 5 or even 6 years, but not nearly on the scope or scale that you guys are doing it. I just don't think they had enough funding, but they were working in this area. The thing that always strikes me as missing is that the characters are too rational, and people are not rational. They're irrational. And they're not only irrational, but they are irrational in a predictable way. And in fact, this is being discovered by economists now, and books on economy are coming out talking about the predictable irrationality. And I guess my question is, are you guys sort of aware of that and trying to fold that into your characters? Because they always seem artificially rational to me. So the elder here, I would just think that he would maybe dig in and simply be stubborn because he's not getting his way. And human properties like that seem to need to be included in the work that you're doing.
So the book that you're referring to is, in fact, right now in my backpack.
This is the
predictable irrationality.
Oh, okay. Yeah.
Yeah.
I've seen that.
And so yes, that is a trend that we're definitely, a thing that we're definitely looking at. The other thing I'll say is that when you change the parameters a little bit, the going in parameters, for example, if you change the level of trust that the doctor or the elder has, you can have the negotiation go from being easy to challenging to impossible. And in fact, these characters, depending on their, for example, their level of trust, they can exhibit remarkably different behaviors as the scenario unfolds. We wanted to, in putting these little video clips together, we wanted to have a successful negotiation and reasonably quickly. But most people, when they initially encounter the doctor, fail in the negotiation because there are certain things that they don't do, like essentially go through an initial phase of small talk to kind of butter him up and all of that. And if you don't do that, it doesn't go well. So, I mean, I think that what you're bringing up is that there's a very rich set of things that are involved in modeling human behavior. We are totally in agreement, and we're trying to essentially knock these things off incrementally. I mean, I think this is something that very much lends itself to scientific study.
Seems like you've had this great vantage point over the last 8 or 9 years to see not only the technologies, the underlying technologies evolve, but also the integration of them evolve. And you've also been able to see the rate at which the change happens. And I wonder if you can take that experience and sort of speculate 8 or 9 years from now what deployable systems will look like?
Well, I think, you know, 8 or 9 years from now, I think we will really have characters that look quite photoreal, much more photoreal than the ones that you know, we're seeing here. I think the animation capabilities and the gestures will also start to track, so that, you know, they're getting better. Certainly better. You can see over the last 9 years, you know, significant improvements. I think you'll see a lot more, so that they really start to look very, very natural. And the interesting thing is, I think, you know, given current trends in computing power, that it'll be possible to have these on, you know, ever cheaper devices as time goes by. So I think you will start to see, for example, in commercially available games, things that you know, look a lot like what we're seeing here now, or better than that. And you'll start to see a lot of these driven by real AI as opposed to game AI, which people sometimes distinguish.
So one question I have is, sometimes there's two ways of looking at the construction or design of a virtual environment. One is to make it indistinguishable from reality, so it's highly realistic. And the other is to go sort of the illusion of life route, where you're not working towards complete fidelity in reality, but you have a different sort of pragmatics behind the design. And they're not necessarily incompatible. You see mixtures of both, but I'm wondering how each informs the work that people at ICT do.
It ideally, when we figure out which way we're trying to, there's actually sort of multiple answers to that question. One is that I think from a research standpoint, and just strictly from the standpoint of developing the technology, one of the things we're always trying to do is push the edge of what's possible. So, you know, through Paul's work and the work of some of the other folks, we're really trying to see how real can we really make these characters or these environments look. And so that's a question of exploring the capabilities and how far you can push it. Then the other thing that you're bringing up is that when you're developing a particular application, there's a judgment call. And you have to decide for that application and for the pedagogical goals that you've got in mind, the things you're trying to explain to people, you know, what's the right level of reality to choose. And it's much like the question that a filmmaker might ask themselves when they're doing the art direction for a film. Do we want this to, you know, is this going to be an animated film, or do we want this to be, you know, live action, or what, or a mix, or what, you know? And there it really depends a lot on the nature of the system. I was talking today with someone about using simulated environments for children with autism. And one of the things that's interesting about children with autism is that they really like anime, which, if you think about it, are characters that have are essentially iconic in their emotional reactions and other things. And the reason why people think that they like anime is because it's much easier to read their expressions and their reactions to things. So if you were building a system, for example, to be a therapeutic system for children with autism, might be that the right approach to take is something that's not photoreal, but instead. So that's just a sort of an obvious example of, you know, the kind of choice that you get into in putting these things together.
Now that I got my question in, we can have one more question. If there's anybody from the floor.
Can you use this to train people to do intellectual tasks or things that don't naturally involve drama, like integration, symbolic integration, or things like that?
Well, there's been, we haven't done that work. You know, John Anderson has done a lot of work on tutoring systems that are involved more with intellectual tasks. There are things like algebra tutors and geometry tutors and things like that. It's not been a focus for us, but I think that certainly the coaching abilities and all that are things that you can use for other more intellectual tasks. Good. Thank you.